right here. So we're working on this problem right here, and I have started it. We're going to try to write it as a b to the x. So we're trying to pull this stuff apart and simplify. So we're working on it right now. I'm going to pause the video. So if you're doing this at home, you can work on it as well. And then you might want to pause it here as well, give yourself a chance to get started on that. So what we're trying to do here is that's going to become a 9. The 8's to the 4/3, since 8 is 2 to the 3rd. And our 3's will cancel and we'll get 2 to the 4th, which is going to be 16. And then we have to pull that apart more. So we can write the 1/16x as 1/16 to the x, because 1 to the x is just the 1, and there's our 16 to the x in the bottom. So we can see that we have our a is the 9 and the b is the 1/16. Crazy, but for fun. All right. Questions on homeworks? Questions on this? Do we need any more clarification on that? There's a different way of doing that. Those are, I think, good algebra skills that will serve us well. So, Katrina.
27.
Okay, do you know what page that is?
No.
Okay, so that's the last homework we did, so I think that's going to be
11.
4.
I think it's on like what's on page 67.
Yep, okay, and what number was it?
11.
11, so that's going to be at page 167, number 11. And let's see what that's asking us. So, what are the nominal and effective annual rates for an account paying the stated annual interest compounded, and then it says A is annually, B is quarterly, and C is daily. So A annually, B is quarterly, and C is daily. And we are looking for nominal and effective annual rates. So 11 is telling us 1%. So I think what they're intending us to do there is make this the nominal rate. And so then on this one, for annually, the nominal rate is going to be the same. So that is still going to be 1%. On the quarterly, what we're going to do is we're using our formula for compound interest. But what we really want to know is how much do we pay in 1 year. So we don't really care about the P, and we don't really, well, the T is going to be 1. So some people like to think of it as being P is 1 and T is 1, or you can just, if you want, ignore the P and the T and just look at this part right here, because this is what is going to multiply our P, our starting amount, in 1 year. So if we're doing this quarterly, we're going to get 1 plus, we're going to change that 1% to 0.01, and our N is going to be 4, which appears in the denominator underneath the R, and also in the exponent both. Okay, now we're going to put this into our calculator, and then we're going to figure out what the R is, and would we expect that to be bigger or smaller than actually 1%?
Bigger.
Bigger because of the compounding. Okay, so if you want to throw that on your calculator and maybe tell me 5 decimal places once you get it there. We have it.
1.01003.
1.01003. Does that look right? So this now is
0.004, I think sounds right.
4 if we round.
Yeah.
Okay. So is that looking right? Heidi, you confirming that? Okay. So then if we subtract off the 1, we're getting 0.01004. And then as a percent, if we move that over, we're getting 1.004%. So that is the effective annual rate. Not huge, because we were starting with such a small percent in the first place. Then to do it daily, we repeat this idea, but now we're going to plug in, for the ends, we're going to plug in 365. That seems reasonable. So we'll get the 1 plus 0.01 over 365 raised to the 365 power. And let's do the same thing. When you get it, you can go 5 places past the decimal. Heidi, you have it already, or Katrina, you have it? No?
Yes, it's 1.01005.
005. So now we can, again, this is our 1 plus r, so we can subtract off the 1 and then make it into a percent. And so it's a little bit bigger, not earth-shatteringly so, but we've gained a little bit over where we were before through the compounding. Does that make sense? Any other questions?
Can we do 19C?
19C. You know what that is, or do I need to?
Should be on page 168.
Okay, so 19C. So it says, if you need $25,000 6 years from now, what is the minimum amount of money you need to deposit in a bank account that pays 5% annual interest compounded, and C is daily. So we want 25,000, and we're going to get 5% is our nominal. Right, so we have 25,000. We have 5%, and we want to make this daily interest. And our goal is to say, so what's the minimum amount if we want the 25,000? So we want to end up with this. So we're looking for what is our original amount. Is that okay?
Yeah.
So in our formula, A equals P times 1 plus R over N to the NT. You don't have to memorize this. I'll give this to you on the test. You just have to know how to use it. So our amount is going to be the 25,000. The P is what we're trying to look for. We're going to go 1 plus, and the R is going to become 0.05. Good. And the N is going to be 365. And now it gets kind of weird because we're going to get 365. Oh, we told the number at one time? We were.
Was it 6 years?
You're right, 6 years. So that's going to be a times 6. Now, if you have one of the newer calculators that moves this exponent up there, you can do the multiplication in there as part of the problem. And the older models where it's on the same line, you would have to put in parentheses and show that multiplication to do that right. But we can actually do this with one calculator entry, which I would really encourage you to do, because it's easier to kind of troubleshoot if you don't get the right answer. It's easier to see where you made your mistake than when people start, doing part of the problem, hitting enter, doing another part of the problem, enter. Then it's harder to track down where you might have made a mistake. So we can actually divide the whole thing over. We'll go 25,000 divided by, and then we'll have this 1 plus 0.05 divided by 365 raised to the 365 times 6. And you can put all of this as one calculator entry into your calculator, and then see what we get. Did you get it?
Yeah, I got 18,520.83604.
836. We'll round to the nearest penny then. Did you get the same thing, Paige?
Yeah.
Okay. Good to go? What else? Okay. Well, today we're going to talk about Euler's number, a surprising number that turns up in very surprising places. So this is section 4.5 in our book. this is that number E that is so important in higher level math for reasons that'll become clear next year in calculus, that it just is, it seems to be everywhere. So Euler is this, one of the giants in math that lived in the 1600s, I think late 1600s, early 1700s. Swiss mathematician. He was just absolutely brilliant, and moved to Russia early in his life and lived most of his life in Russia. He spoke many languages. He went blind in the last 15, 20 years of his life. It didn't slow him down a bit because he had this unbelievable ability to do huge calculations and hold them in his head. They say he could do square roots to several decimal places in his head. Just amazing, amazing person. He wrote and had an impact in virtually every part of math. So he's a real giant, if not the greatest mathematician of all time. I think he makes everybody's top 3 list. So, and amazingly, a lot of the really brilliant mathematicians, you know, they say that line between genius and insanity, a lot of them kind of walk that line, but he, by all reports, had a great family life. He had a bunch of kids and grandkids and was apparently well-liked, which isn't always the case with some of these famous mathematicians. Anyway, this number E is, you know, it's chosen, it's called E because of the first letter of his last name. So he discovered this. Keep in mind, there were no calculators or anything back in his day. So it's surprising that that it comes up in the discussion of compound interest. So we know that our formula for compound interest is P times 1 plus R over N raised to the NT. We have seen that as N gets bigger, you get that nominal rate that we start with. So whatever nominal rate we start with, 5%, 4%, 12%, whatever, the more times you compound it, the larger the effective annual rate. So the question comes up is, how far can you push it? So if you start with, say, 4% interest, what's the most you could get out of that 4% by compounding? So we've seen that as you increase this from 4 times to 12 times to 365 times a year, the compounding, you get a little bit more return each time. So then the question comes up, well, what's the most you could get? What if you took an infinite number? You compounded it like every second or every tenth of a second or whatever. If you could somehow let the N go to infinity, what would you get? What's the most you could get out of that particular percent? And surprisingly or not, if you had seen it in Algebra 2, it leads to our A-curves. It turns out that this brings up that Euler's number. So who would have thought that this strange number, and you can put it on your calculator. If you just do E to the first, why don't you do that real quick and see what we get. And I'm going to do it on here as well. I'm going to turn my calculator on. We'll see a little bit of where this comes from. We're not going to do a ton with it, but I'll just show you how it ends up impacting impacting this compound interest formula. Not everything twisted up. So if you go second ln to the first and then just hit enter, so you can see this is our calculator's best approximation. So I got 2.71828, and it goes on and on. 2.71828. So this is an irrational number, like pi. It's a decimal that never terminates, never repeats. It goes on and on and on. So what's surprising is what Euler figured out back in his day is that the limit as n goes to infinity of 1 plus 1 over n raised to the n is actually equal to that Euler's number. So this, and we haven't done very much with limits. We just introduced this notation a couple days ago. So this is all very new and different for us. But the idea is as n gets bigger and bigger, as you plug in numbers like 100, 1,000, 1,000,000, you have these kind of competing forces. Because on the one hand, as you put in bigger and bigger numbers, like 1,000, 1,000,000, 1 over that gets really, really small. It's getting really close to 0. And you know that 1 plus 0 is 1, and 1 to any power is just 1. So on the one hand, because this is getting smaller and smaller, as n gets bigger and bigger, this seems like it's getting pushed closer and closer to 1. On the other hand, this is never going to be exactly 0. It's always going to be something a little bit bigger. And so 1 plus that is going to be a little bit bigger than 1. If you take a number that's bigger than 1 times itself, it gets a little bit bigger. And if you do that over and over and over and over again, it gets bigger and bigger and bigger. So on the other hand, there seems to be a force acting on this that is pushing this to grow large without bound, to approach infinity. And so you have these competing forces. On the one hand, is that going to get closer and closer to 1? On the other hand, is it going to blow up and get large without bound? And so what's remarkable is that it kind of meets at sort of a place in the middle, not really in the middle. And why it turns out to be this is remarkable.
So,
And how he could figure that out without the aid of a calculator.
does that mean if you graphed it, it would have a vertical asymptote?
Well, so this is pretty tough to graph. Let's do this. I'm going to put this in as a function, y1 equals this. So we're going to put in y is equal to parentheses 1 plus 1 over x to the x power. So do that with me there. I'll do it with you, I guess. So I'm going to go y equals, and I've got old stuff that I'm clearing out. So I'm going to go parentheses 1 plus 1 divided by x, in parentheses raised to the x power. Okay, once you have that in, let's go back to the home screen. So we're going to go second mode. Oh, I want to leave. I'm going to leave up. I'm going to put back up there. I just cleared it off. So I'm going to go back and put the calculator's version of Euler's number on there because I want to have that as a comparison. Now we have this in our calculator, this 1 plus 1 over x to the x. So let's go and evaluate that at, say, 1,000. So we're going to go variables, right arrow, enter, enter. So there's our y1, and go parentheses, and go 1,000 in parentheses. So this is how close this has gotten now. This thing that's going to converge, we say, that's going to get closer and closer to Euler's number. So at 1,000, it's 2.716. So kind of close, but not really obvious that that's what it's going to yet. So this approaches Euler's number, we would say, very slowly. So let's jump to 1 million. You see what I'm doing? Misha, you okay with that? Now I'm going to go back and evaluate it at 1 million.
I was just going to put in like a bunch of zeros.
Yeah, a bunch of zeros. Good call. So I'm going to go back to variables, right arrow, enter, enter, parentheses. I'm going to put in 1 with 6 zeros. So 1, 1, 2, 3, 4, 5, 6 zeros. That's 1 million. And now we can see, now it's getting closer. We got 2.71828. So we've matched it to 5 decimal places, and then it starts to go off. Does that make sense? And the idea is, as you put in bigger and bigger numbers, you're going to get closer and closer to Euler's number. And eventually, it won't take too long before you've hit all the decimal places that our calculator displays, which still doesn't mean it's an exact match. That's just what our calculator has the ability to distinguish. Does that make sense? Okay, so that's our idea of conversion. So knowing that little bit, so if we believe, hopefully I can convince you, that this in fact really does approach Euler's number. So now let's look at taking our compound interest, and we're going to formula, and we're going to say, let's take the limit as n goes to infinity of this p times 1 plus r over n raised to the nt. Now, we are just very much novices in this whole limit stuff. So there's some properties of this that I'm going to do here that we haven't really talked about, but trust me, I'm not lying about this. This is still legal mathematically. Okay, so I'm going to pull the constant p outside and say that's p times the limit as n goes to infinity of 1 plus r over n raised to the nt. Now, what I'm going to do is what's called a change of variables. So I'm going to say k is equal to n over r. that what I want? So let me make sure I'm doing that right. Yep, k is equal to n over r. Now, when you look at these two things, as n goes to infinity, and we're going to pick some particular interest rate, 4% maybe, and we're going to leave it as 0.04 throughout this whole process of taking the limit. Or we're going to pick it to be something else, 10%, whatever. But once we choose the r, it's not changing. It's not a variable. The n is what's changing. So as n gets bigger and bigger and bigger, and r is just stuck being whatever it is, the k is also going to go to infinity. That makes sense? So I'm going to change the variable from n's to k's. So I'm going to say this n is going to be, if I multiply that over, it will be r, no, let me do it this way. So this is going to be, I'm going to change that to the limit as k goes to infinity, right? Because that's still going to force n to go to infinity. And then I'm going to make this 1 plus. So this r over n, I'm going to change in the n for rk. I think that's what I want. Is that what I want? I think so. So that's going to be 1 over k, because that's going to cancel with the r. Is that okay? Oh, I'm getting that blank look I don't like there. So what I'm going to say is that n is equal to rk. So this r over n is going to be r over, and I'm going to replace the n by rk. And so then those are going to cancel, so that's going to become 1 over k. All right?
Why are we using a k variable
Why?
instead of just r over n?
Because what I want to do is I'm going to try to manipulate this so that I can get to here. So I'm going to get to 1 plus 1 over k to the k power as k goes to infinity, which is going to be this just with a name change. And so then I'm going to be able to claim that this is actually Euler's number E. That's my purpose here, my underlying plan. And so to do that, to get to there, I need to do this little bit of, it's called a change in variable. But the idea is it's still correct mathematically, because if n goes to infinity, so does k. So I'm changing the appearance, but not its actual value for a purpose. I have an end game in mind here. Is that okay?
Yeah.
So now the n also we said is rk. So I'm going to replace that n by rk. rkt. Is that okay? Then I'm going to do a little bit of properties of exponents. When I left the p off, that's still in front. So it's p times the limit as k goes to infinity. Now, when you, we know that when you raise a power to a power, we multiply those exponents. So I'm going to go right to left. When you have a product of these powers, I can write them as a power to a power. So in particular, I want to separate out this k and do it inside. So this is going to be the limit, and we're going to have 1 plus 1 over k. I'm going to pick that k out and then do that to the RT power. Okay? Just shuffling things around, but not really changing what its value is. So the whole point of this was now what we've got right here is an exact match to what we've got right here. That make sense?
Where'd the p go in the first
I
one?
just pulled it out.
So what about the first one?
This was just talking about Euler's number. I hadn't even really brought up this whole idea of compound interest. And I said, wait a minute, I think if we look at this and we introduce this limit as n goes to infinity, the number of times we compound it, I think we can bring this E into play, and we are. And so this whole thing here that I boxed in green is going to converge to Euler's number. And so what we're getting is that as the number of times we compound interest goes to infinity, our formula is going to kind of morph. It's going to change into P E to the RT, which you probably learned affectionately as your PERT formula for continuous interest back in your Algebra 2 days. But that's where it comes from. So our continuous interest formula, which is really surprising, ends up using this Euler's number E. So, you know, it's, I think, always surprising that somehow this weird number, Euler's number, comes into play when you're talking about compound interest. That seems to have nothing at all to do with this Euler's number thing. What we'll find out next year is that Euler's number has huge advantages over all the others when you do calculus. So it turns out that when you differentiate e to the x or integrate e to the x, whatever that means, but that's what you spend all of calculus doing, this is like our favorite function to work with because it is so easy, much more so than any other power function or even any other function. So what happens is because of that, when you do higher math, once you go to calculus and beyond, you almost always just rewrite exponentials that aren't base Euler's number. You convert them to Euler's number because after that, they're just way, way easier to work with. And you just can't really appreciate that until next year. We're just actually doing that now. We just learned the derivative of e to the x like last week, so it's like, oh, now finally it all kind of makes sense. Now, what happens is this. Well, let's, how am I doing for time? Okay. So what I want to convince you of here first is not something that you're going to necessarily have to do all the time, but I have to make this kind of believable that we are going to go back and forth sometimes between something like, say, y equals 2 to the x, that we can convert that into some kind of corresponding exponential base Euler's number. That we can go back and forth between the two of these. Any exponential that's written with a base not e can be converted into an exact match of an exponential base Euler's method, base Euler's number. With this.
Can it just be like the e root of 2?
Almost. Well, hold on, we'll get to that. You save that thought. You're in the neighborhood, but not exactly right there. So first, let me try to make a convincing argument, okay? And then we'll see how we're going to actually do it. Likewise, anything that's written in as Euler's number, we could convert to something else. So let's look at a graph for a minute. So let's graph y equals 2. Now remember, this Euler's number is like that 2 points, what did I say, 718, on and on and on. So it's a number that's bigger than 2 but less than 3. So if we graph 2 to the x, from what we talked about yesterday, we know it's going to be an exponential growth function, right? If we graph y equals 3 to the x, that also is an exponential growth function. And we talked about yesterday, they're going to share the point 0, 1. And then to the right of the y-axis, the bigger base 3 is going to be a little bit steeper. But to the left of the y-axis, it's going to hug the x-axis a little faster. So I tried to convince you that the way I think of it anyway, it's like closer to a right angle. So e to the x, which is really a confusing idea, and a lot of people, when you're starting out like where you are now, coming out of Algebra 2, it's like this just raises your anxiety level, and it's like, what is this thing? But we are just going to think of it as in between 2 and 3. Right? Since it's bigger than 1, its graph has to be exponential growth. And in fact, it's going to be pinned in between those two. Since it's bigger than the 2 to the x, it's going to be steeper than the blue one. But because it's less than 3 to the x, it's going to be not quite as steep as the pink one. And likewise here, it's going to try to squeeze its way in between there as we hug the x-axis. So the bottom line is we can think of the graph of e to the x just as being another exponential growth function. And so try to not make it seem like it's something way, way exotic or confusing, because we don't want it to be confusing. And then what I want to also convince you of is this idea of equivalence. So you can see that now if you look at these y values here, if you take any y value that is bigger than 1, you can find, when you go to the orange, you can find a place on that orange curve where the y value is equal to that number. Pick any number you want, 5, 2, 3, 100, 6.57, whatever you like. There is a place on that curve, which means there is some x value, I'm going to call it k, so that e to the k is equal to whatever your favorite number might be, or whatever base we might have that's bigger than 1. You with me here? So my, that okay? So you pick any number you want. So pick 2, right? 2's up here. Come over there. So here's 2 coming to the orange. There is a number k, so that e to the k is equal to 2. And you can do that no matter what you pick. 2, 3, 5, 7.7, whatever you like, whatever number you like. Which means that any base, so if you have this y equals 2 to the x, that k will make e to the k equal to 2. So I can convert this exponential 2 to the x, which you may be more comfortable with, but I, as a calculus teacher, would rather have written as e, because I have ulterior motives. I want you to eventually take a derivative of this thing. And so I can say, well, we can take your favorite number 2, but convert it to my personal preference, e to the k raised to that power. So we can do that no matter what. So any exponential that has a base bigger than 1, we can convert to e to the k, where k is a positive number. Misha?
So in order to find k...
We'll get to that.
Oh.
You're always wanting to get the answers. I just want to get the big idea. Now, if you pick a number that's this, what do I want to say? So,
Greater than 0 and less than 1.
yeah, that's what I'm trying. Yeah, I want to pick a number in between here.
0.5.
So 0.5. So here is Aaron's favorite number, 0.5. So imagine now, she says, but I don't have an exponential that's got a base that's bigger than 1. I have an exponential that's got a base between 0 and 1. Not a problem. It's because we can see for that 0.5, that y value 0.5, I can go, now I'm going to have to go to the left of the x-axis to find a point on that orange curve where e to the k is going to be equal to that 0.5. See what I'm saying? So here's the 0.5, right, the y value. There I am on the orange curve. Whatever that value of k is, e to the k is going to equal 0.5. That k, because we were between 0 and 1, that k is going to be negative. So if the number is between 0 and 1, if our base is between 0 and 1, I can still make it equal to e to the kx, but this decay curve, something that's got a base between 0 and 1, the k is going to be negative. So, summarize. What am I trying to say? Yeah, y equals b to the x. Now, if b is bigger than 1, we can convert this b to the x. There is a k that will make that exactly equal, and that k is going to be a positive number. If we have y equals b to the x, but the b is between 0 and 1, so it's a decay curve, we can still get an exact match to y equals k to the x for the right choice of k, but that k is going to be negative. So when we look at y equals e to the kx, we know, let me back up. When we had y equals b to the x, we could tell at a glance if it was going to be growth or decay based on the size of b. b bigger than 1 is going to be growth. B between 0 and 1, a fraction, a decimal, less than 1, is going to be decay. We do the same thing with e to the kx, but now what makes it growth is the k is positive. And what's going to make it decay is that the k is negative. How am I doing? Not well. Keep your eye on the clock. You know time goes slow when you watch it. If somebody just offered to watch the clock so I can get on. I'm just joking with you there. Okay, now, our book does a great job of calling anything in the form y equals e to the something, as they call this k the continuous rate. So as to avoid confusion about when are we talking about interest that's being compounded a finite number of times. What's the annual rate? What's the effective rate? Our book will call this the continuous rate. So when it says continuous rate, you know you're going to be talking about y equals e to that power. So if we have an annual rate of, say, 5%, and let's say an initial value of, say, $100, whatever that is, dollars or whatever it is, then we would write for an annual rate of 5%, our equation, we would say, is going to be A is equal to 100 times, you're ahead of me, 1 plus R, which is going to be 1.05 to the X or T or whatever you want to call it. Now, if we do a continuous rate of 5%, because you're going to see the word continuous rate, now it's not going to be this at all. It's going to be now, A is going to be 100 e to the 0.05x. So you're going to see, just like our PERT formula, that number that is multiplying the x holds the percent increase. If we have a decay curve, so if we have, say, an annual rate and it's going to decay by, say, 8%, and then I'm going to do it a decay continuous at a continuous rate of 8%. So how do these look similar? How do they look different? So now we're talking about something that's decreasing exponentially. So we have said that this, we've been doing the last day or so, we're going to get an equation. I'm going to go back to y's and x's. Y is going to equal still the same initial value, 100. It's going to be 100 times, it's decaying, so it's going to be 1 minus 0.08, which is going to be how much? 0.92 to the x power. Does that make sense? You see it's a decay, it's decreasing because the base is less than 1. What does that look like in the continuous case?
0.92.
What was it? Negative 0.08x. And that's where people get confused. They try to start making this a 0.92. Because remember, this is saying e to the negative 0.8 to the x. That's going to become 1 over e to the 0.08. That's going to be a number that's less than 1. But e to the 0.92, that is not going to be less than 1. That's going to be a growth. Remember, this number is like almost 3. And so 3 to the first would be 3, 3 to a little bit less is still going to be bigger than 1. So you can't make that a 0.92. Okay. Oh, goodness gracious. So let's see how they compare. So 1.05. So this is our 5% annual interest. Annual. And how does that compare to e to the 0.05? This is 5% continuous. They are not exactly the same.
They're really close, right?
Yeah, they're close, but what would you expect to be more? Think about compound interest. Remember, this is compounded how many times a year? Once. This is compounded how many times a year? An infinite number. Which is going to be bigger? This should be bigger, right? Well, throw it on your calculator. E to the 0.05. And tell me what you get. and on and on and on, right? Okay, so it is going to be a little bit bigger, so there's not an exact conversion. So what happens if you want to convert one to the other? Well, if we want to take 1.05 and convert that to e to the k, what are we going to pick for the k? So what continuous rate is exactly the same as a 5% annual rate? How do you solve this? We haven't talked about it in here, but you know it from your Algebra 2 days. How do you solve for k?
Oh, take the E root.
Not the e root,
Logarithm.
a logarithm, base Euler's number, which we call
Natural log.
the natural logarithm, ln. So you're going to take natural log of 1.05 is natural log of e to the k.
Those cancel.
And yet, because a logarithm based Euler's number and an exponential based Euler's number are inverses of each other, that's going to be just k. That is the number you're going to use. Wow.
That's a little.
Time flies when you're having fun. Yes. All right. We will talk more. Believe me.